Welcome, my soft-thinking listener. You've found yourself in the company of the Sleepy Sloth once again. A slow, scientifically minded fellow who enjoys facts, small and big worlds, and things that float patiently in our solar system. I must tell you something before we begin. Today, I consider myself a scientist in planets. A scientist wannabe who is almost always correct, except for those few times when I am not. But even then, I prefer to drift gently onward, rather than fuss over it. Because what truly matters is the information itself. Before I start, please, let me know. What is the most boring thing you would secretly love hearing about? Let me know gently, in the comments. Now, let us begin today's episode with Eris, the dwarf planet. Eris drifts on an orbit that is not a perfect circle but rather a stretched oval, what astronomers call an eccentric orbit. At its farthest, known as aphelion, Eris can be more than 101 astronomical units from the Sun, while at its closest, or perihelion, it draws inward to about 38 astronomical units. This means that during its long 557-year journey, Eris sometimes wanders farther than nearly all other known dwarf planets, and sometimes it actually comes closer to the Sun than Pluto does. Yet even when it is closest, Eris remains an unseen ghost in the night sky, too dim for human eyes without telescopes. Such invisibility is not dramatic. It is merely quiet. A reminder that most of the solar system is content to exist beyond our immediate view. Let us drift a little deeper into its surface story. The bright exterior of Eris is not merely nitrogen ice, but is also believed to contain frozen methane, a simple molecule of carbon and hydrogen that can form a thin frost. Sunlight, faint though it is at 96 astronomical units, can still strike this methane, slowly altering it over millions of years into more complex substances called thlins. These thlins can add a slight reddish tint to the otherwise white glare of Eris. They are not dangerous, nor particularly lively. They are just molecules rearranged by light, lying in patient stillness upon a frozen crust. If one were to stand upon Eris, which no one has, the ground would likely crunch faintly, with icy grains compressed by unimaginable cold, where temperatures may drop to -230 degrees Celsius. Such temperatures are beyond human tolerance, but for Eris, they are natural, gentle, and eternal. Now, let us float once more to Dysnomia, the moon that circles in calm companionship. Dysnomia itself is estimated to be only about 350 kilometers across, smaller than many asteroids, and yet its presence is essential. Without Dysnomia, astronomers would not be able to weigh Eris so precisely, for it is through observing the moon's orbit, its pace, its rhythm, and its gravitational bond, that Eris's true heft was revealed. Dysnomia has no atmosphere, no oceans, no weather. It is a still fragment of rock and ice. And yet, in the empty quiet of space, its devotion to Eris is constant, unbroken, like a clock that ticks only once every 16 days. These are not exciting details. They are merely there. And that is what makes them soothing. Eris spins on its axis as well, completing a day in about 25.5 hours. This is curiously close to the length of a day on Earth, though no sunsets or dawns are visible there in any familiar way. The Sun, so far away, would appear merely as a brilliant star, brighter than the others, yet never enough to warm the ground. Still, a day passes. Night follows day. But the difference between them would hardly matter. For Eris, time itself drifts like frozen mist. And so, we drift alongside it, ever so slowly, in thought and in quietness. A quiet hush drifts through the distant reaches of the Kuiper belt, where Makemake moves along its long, slow orbit, a dwarf planet whose average distance from the Sun is about 45.7 astronomical units. Light from our Sun, the fastest traveler in the cosmos, requires roughly 6 hours and 20 minutes to reach it, a gentle delay that allows the mind to imagine an invisible journey across empty space. This frozen region beyond Neptune is sparsely populated, yet subtly crowded with icy bodies that glide along parallel tracks, each on its own slow path. Makemke's orbit itself is inclined about 28 degrees to the plane of the solar system, a tilt that makes its journey through the heavens appear delicately off-kilter, like a softly swaying pendulum of ice and rock. Thinking about these distances, numbers, and inclinations is not exciting, it is meditative, like counting the soft oscillations of a leaf falling in a shaded forest, or the slow turning of ancient gears hidden beneath dust. A faint sparkle in historical memory reminds us that Makemake was discovered on March 31, 2005, by astronomers Michael E. Brown, Chad Trujillo, and David L. Rabinowitz at Palomar Observatory. For a time, it bore the provisional designation 2005 FY9, a quiet, bureaucratic label that would later be replaced with a name rooted in human myth, Makemake, the creator god of the Rapa Nui people of Easter Island. The choice of name, suggested in 2008, preserves a sense of seasonal timing, as the discovery occurred near Easter, and it allows us to fold cultural meaning into the otherwise silent, icy world. Its classification as a dwarf planet in 2006 emerged from long deliberations among astronomers, as they reconsidered the definition of a planet following the discovery of Eris, Haumea, and other distant bodies. This slow, methodical human decision-making mirrors the languid motion of Makemake itself, drifting almost unnoticed along its orbit, a quiet reminder of the patient rhythm of both space and thought. In the soft imaginings of its surface, Makemake appears almost impossibly bright for such a distant world. Its geometric albedo, measured at approximately 82%, reflects most of the sunlight that reaches it, making it one of the brightest known objects in the Kuiper belt. Its diameter, measured at roughly 1,434 kilometers, is slightly smaller than Pluto, yet still immense when considered in human terms. The surface is largely composed of frozen methane, with minor traces of ethane and possibly nitrogen, forming a thin frost that, over geological time, can transform under ultraviolet radiation into complex reddish molecules called flins. These chemical processes are subtle, patient, and almost imperceptible, slowly reshaping the icy surface with a quiet, unhurried artistry. If one could stand on Makemake, which no human has, one might feel a crunchy frost underfoot, illuminated only by a sun that appears as a small, brilliant star rather than a warming disk. A gentle note of companionship exists as well. Makemake is accompanied by a tiny moon, provisionally designated S/2015, 136,472, 1, and affectionately nicknamed MK2. Discovered in 2015 through careful analysis of Hubble Space Telescope images, this small satellite measures roughly 175 kilometers across, assuming a dark surface, and orbits at a distance of about 21,000 kilometers from its parent. Its orbit, slow and precise, allows astronomers to measure Makemake's mass with remarkable accuracy, revealing a world whose density, rotation, and composition can be inferred without ever visiting it. The relationship between Makemake and MK2 is quiet, dependable, and unchanging, like a clock whose hands move only once every several days, a cosmic reminder that even in the stillness of the outer solar system, patterns and rhythms endure. Far from the Sun, temperatures on Makemake are extraordinarily low, with average surface conditions estimated around 30 to 40 kelvins, roughly -240 to -230 degrees Celsius. Under such conditions, volatile compounds remain frozen in place, while ultraviolet radiation slowly modifies molecules over millions of years. Methane and ethane ices, for instance, can produce faintly reddish hues as they convert to flins, creating a subtle visual texture that telescopes detect as a slightly colored reflection. These chemical alterations are painstakingly slow and entirely invisible to casual observers, yet they provide a small, unhurried record of the interaction between solar radiation and matter at the fringes of our solar system. A whisper of orbital detail encourages patience in understanding Makemake's path. Its semi-major axis of approximately 45.4 AU, combined with an eccentricity that allows the orbit to stretch slightly from near 38 AU at perihelion to over 52 AU at aphelion, forms a gentle, elongated ellipse. This high-inclination orbit carries Makemake above and below the ecliptic plane, where the planets of the inner solar system circle more closely. The orbit's duration of roughly 306 Earth years suggests an entire year on Makemake is longer than most dynasties of human history, a temporal scale that invites contemplation of time itself as slow, patient, and deliberate, moving at a pace imperceptible to human eyes yet exact in its celestial mechanics. Delving into rotation, Makemake spins on its axis once every approximately 22¾ hours, a day length surprisingly similar to Earth's. The rotation is measured from subtle variations in brightness over time, caused by small surface irregularities and variations in reflectivity. Each gentle turn brings a quiet change in which side faces the sun, producing faint shifts in illumination across the icy landscape. This slow rotation, paired with a nearly invisible sun, creates days and nights that are calm, imperceptible, and ultimately uneventful, a cosmic lullaby of subtle illumination and cold reflection. A slow observation of measurement techniques reminds us how careful and precise human study must be at such distances. Photometry, occultation studies, and spacecraft observations each contribute small pieces to a puzzle that is otherwise impossible to observe directly. Occultations, for instance, occur when Makemake passes in front of distant stars, casting a fleeting shadow that allows astronomers to estimate its size and shape. These events are brief, yet the data extracted provides remarkably tight constraints on the dwarf planet's diameter and possible elongation. Each measurement is a quiet triumph of patience, requiring hours of preparation, precise timing, and gentle calculation, yielding knowledge that drifts slowly into the collective understanding of the solar system. A gentle reflection on composition reveals that while methane dominates, minor quantities of ethane, and perhaps nitrogen, exist in localized regions. These ices respond subtly to minimal heating when Makemake nears perihelion, potentially forming a transient atmosphere that quickly freezes back onto the surface as it recedes. Such processes are imperceptibly slow, cyclical, and quiet, creating no gusts, storms, or dramatic displays. The interactions are molecular, chemical, and patient, a careful dance over millennia that leaves the planet mostly unchanged yet subtly evolving, preserving its high albedo and pale reddish color. A soft consideration of brightness and visibility drifts onward. Makemake's high reflectivity, measured at over 80%, makes it one of the brighter Kuiper belt objects, though it remains invisible without telescopic assistance. From Earth, it appears as a faint point of light, its brilliance diluted by distance, yet steady in position and predictable in motion. This constancy is not flashy or urgent. It is a gentle affirmation that even distant, nearly invisible worlds maintain order, reflecting light quietly, reliably, and without fanfare across billions of kilometers of space. A delicate note on comparison whispers softly, Makemake is slightly smaller than Pluto in diameter, yet it is similar in other ways, sharing a lightly reddish surface, slow rotation, and high reflectivity. Its orbit is less eccentric than Eris but more inclined than Pluto, providing another contrast to its distant cousins. By observing Makemake, scientists can gently extrapolate characteristics of other Kuiper belt objects, building a soft, interlinked picture of the far reaches of our solar system, one quiet fact at a time. The exploration of Makemake, though purely remote, continues to expand. Telescopes and spacecraft like New Horizons have provided glimpses, phase angle measurements, and photometric studies, each contributing subtle refinements to size, shape, composition, and reflectivity. Every new observation requires careful analysis, repeated measurements, and patient cross-referencing with older data. This slow accumulation of knowledge mirrors the icy, patient nature of the dwarf planet itself. Nothing hurries, nothing demands attention, and yet each small piece fits together to form a gently coherent understanding of a world far from the sun and far from human presence. A final cluster of contemplative facts rests softly: Makemake mass, rotation, surface composition, brightness, and orbital parameters are all estimates informed by careful study and repeated observation. Uncertainties remain, acknowledged politely by scientists, who report ranges and probable values rather than single definitive numbers. The dwarf planet exists independently of these measurements, undisturbed by human curiosity, yet our knowledge expands incrementally with each patient observation, like slowly unrolling a soft carpet of facts across the dark, frozen floor of the Kuiper belt. Each new insight, minor or major, adds a gentle texture to our understanding, a quiet rhythm in the slow symphony of the outer solar system. A gentle ripple of thought drifts across the outer solar system as we consider Haumea, a distant dwarf planet orbiting quietly in the Kuiper belt, roughly 43.2 astronomical units from the Sun. Its orbit, like a slow, elongated ellipse, carries it just beyond Neptune, yet slightly closer than Makemake or Eris, and this distance allows sunlight to take about 5 hours and 59 minutes to travel the empty space that separates us from this icy world. The Kuiper belt itself is a broad, diffuse band of icy bodies, many small and largely invisible, and Haumea glides along this frozen river as one of the largest of its kind. Its orbit is tilted at nearly 28 degrees to the plane in which Earth circles, giving it a graceful, angled path that brings it sometimes above, sometimes below the crowded ecliptic, yet always in a patient, steady motion, as if the solar system's outer edges are conducting a slow, quiet ballet. A soft shimmer of discovery drifts to the mind. Haumea was first observed in 2004 by astronomers Mike Brown, Chad Trujillo, and David Rabinowitz at the Palomar Observatory, though independent observations by José Luis Ortiz Moreno and his team in Spain were also made shortly afterward. These observations relied on careful detection of a faint point of light moving slowly against the starry background, a signal so dim and distant that it required patience and exacting measurement. The provisional designation 2003 EL61 was assigned before it received its more lyrical name in 2008, honoring the Hawaiian goddess of fertility and childbirth. Naming this dwarf planet reminds us that human stories and mythologies can be woven delicately around worlds that are otherwise entirely indifferent to our presence. The classification as a dwarf planet came from the International Astronomical Union in 2008, joining the quiet ranks of Eris, Makemake, and Pluto. Worlds that remind us patience, observation, and definition are intertwined in the slow pursuit of knowledge. A drifting thought of shape and rotation brings us closer to Haumea's unusual characteristics. Unlike the nearly spherical forms of many dwarf planets, Haumea is highly elongated, resembling a stretched ellipsoid, a result of its extraordinarily rapid rotation, about once every 3.5 hours. This is an astonishingly fast spin for a planetary body, and it causes Haumea's shape to become more like a flattened rugby ball than a rounded globe. This rapid rotation also means that surface gravity varies across the planet, being slightly weaker at the ends of its elongated axis and stronger at the equator, though the differences are gentle and imperceptible to any wandering particle of dust. The rapid spin likely also contributes to the planet's thin, frozen atmosphere, or lack thereof, since volatile compounds like methane or nitrogen cannot accumulate for long before escaping into space. Each rotation passes unnoticed by any observer, yet to the dwarf planet itself, it is a rhythm as constant and unhurried as the orbit that carries it silently around the Sun. A faint shimmer of companionship enters our thoughts as we consider Haumea's two known moons, Hi'iaka and Namaka. Hi'iaka, the larger, measures approximately 310 kilometers in diameter and orbits Haumea at a distance of about 49,500 kilometers, completing a revolution in roughly 49 days. Namaka is smaller, around 170 kilometers across, and follows a more eccentric orbit, taking roughly 18 days to circle the dwarf planet. These satellites were discovered through careful observations using the Hubble Space Telescope, and their gentle, unchanging paths allow astronomers to calculate Haumea's mass with remarkable precision. Their existence also hints at a dramatic but ancient event. The moons, and indeed much of Haumea's surface, are thought to be the result of a colossal collision that stripped away material from the original body, scattering icy fragments that coalesced into moons and forming a family of related Kuiper belt objects that share similar orbits and surface properties. A drifting sense of cold and frost touches our imagination as we consider Haumea's surface. Spectroscopic studies reveal that it is dominated by crystalline water ice, a detail that is unusually pristine for a body so far from the Sun. This crystalline ice suggests that either a relatively recent collision exposed fresh material or that some internal process prevents the ice from amorphizing entirely under cosmic radiation over eons. Minor traces of methane may also exist, but the surface appears dominated by reflective, water-rich ice that gives Haumea a bright appearance. Its albedo is estimated to be roughly 70 to 75%, making it one of the brighter Kuiper belt objects when viewed from afar. These reflective icy plains shimmer quietly in telescopic observations, not with brilliant color or movement, but with a soft, constant brightness that hints at the composition of the planet while remaining utterly tranquil. A delicate contemplation of orbit and distance reminds us that Haumea's path is slightly elongated, with perihelion at about 36 AU and aphelion around 50 AU. This eccentric orbit stretches and compresses its distance from the Sun over its approximately 283 Earth-year journey, producing slow variations in insolation, though nothing that generates weather or activity visible to distant observers. Its high inclination, combined with this eccentricity, means Haumea travels through regions of space largely unvisited by spacecraft or observed by telescopes, a lonely wanderer in a quiet, icy belt. The interplay of orbital tilt and elongation is slow and predictable, a testament to gravitational mechanics that operate without hurry, maintaining the balance of the solar system at its distant edge. A soft whisper of rotation reminds us again of its unusual speed, which is critical for understanding its shape and density. Haumea's rapid spin is so extreme that it distorts its interior into an ellipsoidal form and affects surface gravity enough to influence the orbits of its moons subtly. Calculating the planet's mass through observations of these moons reveals a density of about 1.885 grams per cubic centimeter, suggesting that its interior is a mix of rock and water ice, a composition that is unremarkable in comparison with other Kuiper belt objects, yet still precise and quietly important for scientists mapping the distribution of materials in the outer solar system. The spin, shape, and density form an interlinked, slowly unfolding story of physics and time, offering a calm and steady rhythm of understanding. A gentle murmur of thermal reality touches the mind. The temperature on Haumea's surface is extremely cold, with models indicating around 30 to 40 kelvins, roughly -240 to -230 degrees Celsius. These temperatures are sufficient to keep water ice solid, as well as other volatiles frozen for millennia. The crystalline nature of Haumea's water ice implies a history of collisions or resurfacing events, for otherwise cosmic radiation would gradually amorphize the ice over billions of years. The interplay of temperature, spin, and surface composition is subtle, slow, and entirely silent, producing conditions that are stable, calm, and uneventful, a landscape frozen in a quiet equilibrium that has persisted across the slow passage of centuries and millennia. A soft observation of human study reminds us that all we know about Haumea comes from patient measurement, photometry, spectroscopy, occultations, and spacecraft observations contribute small, precise pieces of data, each carefully analyzed to infer size, shape, spin, composition, and orbital characteristics. Occultations, where Haumea passes in front of a distant star, provide especially accurate constraints on the dimensions and shape of the dwarf planet, revealing the extreme elongation and allowing calculations of volume and density. Each measurement requires meticulous care, repeated observation, and consideration of uncertainties, producing a slow, layered understanding that drifts gradually into the collective human knowledge, much like a feather settling onto soft moss in a quiet forest. A drifting note of moons and ancient collisions adds quiet texture to the narrative. The presence of Hyakka and Namaka, along with other family members in dynamically related orbits, suggests a catastrophic collision early in Haumea's history. This event likely stripped away outer layers, producing fragments that formed its moons and other related Kuiper belt objects. Evidence for this family comes from shared orbital parameters and surface properties, a silent cosmic footprint that hints at violent events that occurred billions of years ago, yet are now frozen into the long, calm journey of the planet. These traces of ancient chaos exist only as gentle whispers in spectral measurements, offering insight without drama, a soft story of cosmic recycling that emphasizes time, patience, and distance. A delicate reflection on visual appearance follows. Haumea, though small, shines brightly due to its high albedo, reflecting most of the faint sunlight it receives. Its reddish tint is weaker than Makemaka's, attributed to smaller amounts of lens and surface processing by cosmic radiation. Viewed through large telescopes, it appears as a faint point of light that shifts imperceptibly against the background of distant stars, predictable and serene, a reminder that even the quietest objects in space have precise, measurable behaviors. The dwarf planet's calm brightness and consistent motion provide a steady reference point in the outer solar system, allowing astronomers to trace orbital dynamics across decades of observation. A soft consideration of rotation, moon orbits, and internal structure completes a quiet understanding of Haumea. The fast rotation, highly elongated shape, moon's orbits, and inferred rock ice interior combine into a coherent, slowly unfolding picture of a distant world. Its journey is long, quiet, and unchanging from our perspective, yet precise and measurable for those willing to observe carefully. Each new measurement adds detail, each new model adjusts understanding, and each slowly drifting orbit confirms the gentle rules of gravity and motion that govern the solar system's distant reaches. Haumea is patient, exact, and quietly persistent, a distant participant in the slow, grand choreography of the Kuiper belt. A gentle hush settles over the distant reaches of the solar system as we drift our thoughts toward Neptune, the eighth planet, a colossal ice giant circling the Sun at an average distance of about 30 astronomical units. At this separation, sunlight travels slowly, taking roughly 4 hours and 10 minutes to bridge the vast gulf of nearly 4.5 billion kilometers, a journey imperceptible to us but steady and unwavering. Neptune's orbit is a graceful ellipse, inclined only slightly, by about 1.77 degrees, to the plane in which Earth and the other planets revolve. Its motion is patient, measured, almost meditative, tracing a precise path shaped by the gravitational presence of its neighbors, especially Uranus, whose interactions have subtly nudged Neptune over eons. The space around Neptune, though sparsely populated by small icy bodies and the occasional distant Kuiper belt object, is a silent corridor where the planet drifts with little disturbance, a massive, serene presence cloaked in clouds of methane and other frozen compounds. A soft, drifting thought guides us to Neptune's discovery, a tale of calculation rather than casual observation. In 1846, Johann Galle and Heinrich de Rest observed Neptune for the first time, using predictions made by Urban Le Verrier, who carefully calculated perturbations in Uranus's orbit. This quiet, almost invisible tug in the motion of another planet led astronomers to pinpoint a location in the sky where Neptune must exist, a triumph of patient mathematics rather than striking visual observation. Its discovery illustrates the slow, meticulous dance between human calculation and cosmic reality, where unseen forces hint at distant worlds long before the first telescope glimpses their subtle light. Neptune itself, indifferent to our measurement, continued on its orbit, silently validating calculations made by minds far away and decades before space travel made any approach possible. A soft curtain of clouds drifts across our imagination as we consider Neptune's atmosphere, composed primarily of hydrogen, helium, and a small but crucial portion of methane. The methane is what gives the planet its characteristic deep azure hue, reflecting sunlight in a delicate, steady blue that contrasts softly against the black backdrop of space. Layers of clouds exist at varying altitudes, composed of frozen methane, ammonia, and possibly water ice, forming a series of calm, diffuse layers that slowly shift over time. Wind speeds, though astonishing by earthly standards, reaching up to 2,100 kilometers per hour, are spread over immense distances, moving with an elegance and uniformity that feels like a slow, endless river of gas around the planet's mid-latitudes. These winds shape faint banding and subtle cloud features, patterns that telescope observations and spacecraft images reveal, though they remain gentle and almost unnoticeable to casual sight. A drifting sense of rotation reminds us that Neptune completes one spin on its axis approximately every 16 hours. This rapid rotation, coupled with its vast diameter of roughly 49,200 kilometers, produces a flattened shape at the poles, creating a subtle equatorial bulge, gentle in form but precise in measurement. The planet's interior, largely composed of ice and rock overlaid by dense hydrogen and helium gases, is thought to be warmer than the upper atmosphere, allowing slow convection currents to rise and fall in the thick gaseous layers. These convective motions, while invisible to our eyes, influence cloud formations and weather patterns, maintaining a quiet, steady rhythm that repeats endlessly. The interior itself is a layered composition of hydrogen, helium, water, ammonia, and methane ices, producing a complex yet tranquil structure that has persisted for billions of years. A slow and careful consideration of Neptune's moons introduces quiet companions that circle in stately orbits. Triton, the largest, measures roughly 2,710 kilometers across and follows a retrograde orbit, unusual among large moons, hinting at a captured object rather than a co-formed satellite. Triton's surface is coated in frozen nitrogen, with regions of water ice and subtle traces of methane, creating a smooth, reflective exterior. Geysers have been observed erupting small plumes, likely driven by internal heat and solar sublimation, though these phenomena are subdued, occurring quietly in the planet's distant orbit. Other smaller moons, including Proteus, Nereid, and Larissa, drift along elliptical paths, each providing slight, steady gravitational interactions that contribute to the intricate balance of Neptune's system. The slow, predictable motion of these moons creates a sense of calm order, a measured cadence in a system otherwise invisible to our immediate senses. A soft reflection on Neptune's magnetosphere reveals a field tilted approximately 47 degrees from its rotation axis, and offset from the planet's center. This unusual geometry produces a slowly varying, asymmetric magnetic environment, influencing charged particles in subtle ways and creating faint auroral glows near the poles, visible in ultraviolet imaging. Unlike Earth, these auroras do not flash dramatically or erupt violently, they shimmer gently, tracing the movement of electrons in a quiet ballet around the polar regions. The magnetic field itself is generated by convection in a layer of electrically conductive fluids deep inside the planet, most likely a hot, ionic mixture of water, ammonia, and methane, slowly circulating and producing a continuous, steady geomagnetic effect. A drifting thought on thermal energy reminds us that Neptune radiates more energy than it receives from the Sun, emitting about 2.6 times as much. This excess heat originates from the slow contraction of the planet's interior and the gravitational energy released as it formed long ago. The flow of this heat is gentle and consistent, driving subtle convection in the mantle and atmosphere, maintaining clouds, storms, and the faint banded features that mark the surface. Unlike solar-driven weather on Earth, Neptune's energy source is internal, quiet, constant, and deeply unhurried, providing a subtle engine for planetary activity that has persisted over eons without interruption. A soft ripple of orbiting debris reminds us that Neptune is shepherd to the Kuiper belt, influencing objects through gravitational resonance. Pluto, in a 3:2 resonance, and other bodies are gently held in place by Neptune's consistent gravitational pull, maintaining order in the distant, icy reaches. The planet's distant influence creates a quiet structure to the outer solar system, a stabilizing presence that prevents chaos from dominating the small, wandering bodies beyond its orbit. This role is slow, invisible, and yet measurable, offering another example of the calm, precise effects that a massive planet exerts over long distances in space. A reflection on historical exploration allows us to imagine Voyager 2's brief encounter in 1989, when the spacecraft passed within 4.95 billion kilometers, sending back images and data that transformed our understanding. The observations revealed faint cloud bands, the Great Dark Spot, a massive storm system at the time of encounter, and a variety of smaller cloud features, all moving across the planet's upper atmosphere. Each measurement, from wind speed to temperature profile, was painstakingly gathered, digitized, and analyzed over months and years, a patient accumulation of knowledge that transformed a distant blue dot into a richly characterized world. Even the Great Dark Spot disappeared by Hubble observations a few years later, illustrating the quiet, transient, yet slowly evolving patterns of Neptune's meteorology. A drifting thought on density and composition provides further calm detail. Neptune has a mean density of approximately 1.638 grams per cubic centimeter, less than Earth but indicative of a significant ice component beneath a gaseous envelope. Its composition of hydrogen, helium, water, ammonia, and methane forms an ice giant rather than a gas giant, distinguishing it from Jupiter and Saturn. The distinction is subtle and mostly of interest to astronomers, yet it speaks to the different formation histories, internal structure, and thermal dynamics that make Neptune unique among planets in the solar system. Each layer of ice, rock, and gas is in quiet equilibrium, slowly circulating, interacting with gravitational forces and solar energy, producing a harmonious, unhurried planetary body. A soft meditation on winds and storms drifts across the mind. Neptune's winds are the fastest in the solar system, yet they flow smoothly over thousands of kilometers, without abrupt stops or jerks. Speeds exceeding 2,100 kilometers per hour shape cloud patterns, yet this motion is evenly distributed across latitude bands. Storms, such as the former Great Dark Spot, drift slowly westward, maintained by subtle energy from internal heat. Even when observed as extreme, these winds and storms are gentle on a cosmic scale, moving across an invisible ocean of gas, creating a rhythmic, predictable, and quiet choreography that has persisted through centuries. A gentle consideration of planetary tilt and seasonal cycles follows. Neptune's axial tilt is about 28.32 degrees, similar to Earth's, producing subtle seasonal variations over its long orbital period of roughly 164.8 Earth years. Each season spans over 40 Earth years, a length of time that emphasizes the quiet, patient unfolding of planetary processes. Temperature differences are modest in the upper atmosphere, and cloud activity slowly waxes and wanes, producing nearly imperceptible shifts in appearance over decades. Observing Neptune's seasonal rhythms is a meditation in patience, requiring long-term data collection and careful comparison, revealing slow changes that are comforting in their predictability rather than dramatic in impact. A drifting observation of Neptune's ring system adds another layer of quiet fascination. Though faint and composed primarily of dark dust particles, the rings, Gaul, Leverrier, Lassell, Arago, and Adams, maintain steady positions, sculpted by small shepherd moons. These narrow, faint bands are invisible to the naked eye, revealed only through telescopic imaging and occultation studies. Their stability over centuries illustrates the quiet gravitational dance of small bodies in Neptune's orbit, a subtle addition to the serene, layered complexity of the planet's outer environment. A gentle, lingering sense of distance drifts across our thoughts as we turn toward Pluto, the small, icy dwarf planet quietly tracing its path in the Kuiper belt, at an average distance of approximately 39.5 astronomical units from the Sun. Its orbit is subtly elliptical, bringing it closer to the Sun than Neptune at certain points in its journey, a rare overlap that occurs roughly every 248 Earth years. Light traveling from our star takes about 5 hours and 32 minutes to reach Pluto, a slow, deliberate journey through the near-empty void, barely noticeable yet profoundly exact in its passage. This elongated orbit carries Pluto through regions of the Kuiper belt populated by distant, icy objects, each drifting with patience over billions of years, creating a calm, silent background to the slow revolutions of the solar system's outermost worlds. The plane of its orbit is tilted by approximately 17 degrees relative to Earth's, adding a gentle inclination to its otherwise steady path, a small tilt that allows the dwarf planet to rise above and dip below the ecliptic in a rhythm that is slow and unhurried. A soft, contemplative thought drifts toward Pluto's discovery, a story woven from careful observation and patient calculation. Clyde Tombaugh first identified Pluto in 1930 at the Lowell Observatory, after methodically comparing photographic plates over consecutive nights, noticing a faint point of light that shifted imperceptibly against the fixed background stars. The identification of this tiny, distant object was less a sudden revelation than a quiet triumph of perseverance, measurement, and methodical attention to minute motion. Pluto was initially considered the ninth planet of the solar system, a classification that endured until the early 21st century when definitions of planetary status were reconsidered in the presence of similarly sized and more massive Kuiper belt objects. Its reclassification as a dwarf planet in 2006 by the International Astronomical Union did not change its orbit or composition, only our human understanding of planetary hierarchy, a reminder that knowledge drifts slowly, quietly evolving as observations and criteria accumulate. A drifting layer of icy composition emerges in our thoughts as we examine Pluto's surface. Spectroscopic observations reveal a terrain composed primarily of nitrogen ice, with notable contributions from methane and carbon monoxide ices. These compounds create a patchwork of reflective plains and darker regions, forming subtle contrasts that give Pluto its variegated appearance. The region known as Sputnik Planitia, a vast nitrogen ice plain, exhibits evidence of slow glacial flow and convection patterns, a process imperceptible in the span of human life yet measurable over decades by careful observation and space missions. Methane-rich regions contribute to reddish hues, while nitrogen ice remains bright and reflective, giving the dwarf planet a soft, ghostly luminescence when viewed through telescopes. Temperature measurements suggest a frigid environment, around 30 to 45 kelvins, or roughly -240 to -228 degrees Celsius, maintaining these ices in a solid state across the eons. A subtle ripple of moons drifts into focus, for Pluto is accompanied by a complex family of satellites. Charon, the largest, measures about 1,212 kilometers across, more than half the diameter of Pluto itself, and orbits with precise synchronization, creating a barycenter outside Pluto's own body. This mutual orbit produces a slow, stately dance, an almost imperceptible balancing act in which each gravitational tug is gentle, continuous, and extraordinarily stable. Smaller moons, Styx, Nix, Kerberos, and Hydra, follow wider, more distant orbits, their sizes ranging from roughly 10 to 70 kilometers in diameter. The discovery of these moons, particularly through the Hubble Space Telescope, allows astronomers to measure Pluto's mass and density with care, revealing a density of approximately 1.88 grams per cubic centimeter, indicative of a mixture of ice and rock. Each satellite's motion is calm, predictable, and elegantly orchestrated, a quiet testament to gravitational choreography in the outer solar system. A flowing consideration of Pluto's internal structure invites reflection on the slow, hidden mechanics beneath its surface. Models suggest a differentiated interior, with a rocky core surrounded by a mantle of water ice, overlain by volatile ices. The core may reach temperatures sufficient to maintain subsurface liquid water, insulated by the overlying ice and thick nitrogen and methane layers, creating the potential for slow, creeping movements within the interior. This layered structure contributes to Pluto's subtle geological activity, observed as tectonic-like features, ice ridges, and fault lines across the surface, all forming without dramatic upheaval, as though the planet's frozen heart beats in a long, gentle rhythm. Internal heat, derived from radioactive decay in the core, flows outward in minuscule, steady amounts, insufficient to melt surface ices but enough to maintain slow internal motion that manifests over millions of years. A drifting thought of atmosphere brings a delicate layer of tenuous air to mind. Pluto possesses a thin atmosphere, primarily nitrogen, with minor components of methane and carbon monoxide. This atmosphere is highly sensitive to its distance from the Sun, expanding as the dwarf planet nears perihelion and collapsing when it moves farther away. Surface pressure is measured in microbars, millions of times weaker than Earth's, yet it supports gentle sublimation of ices from the surface, contributing to frost patterns and thin clouds. This ephemeral atmosphere is detectable through occultations, when Pluto passes in front of a distant star, allowing careful measurement of the way starlight dims and bends. The atmosphere drifts and fluctuates with calm precision, entirely silent, and largely invisible to human observation, a soft veil of gases wrapping the planet in a quiet, transient shroud. A soft thought of exploration brings us to the brief yet transformative encounter of New Horizons in 2015. The spacecraft passed within 12,500 kilometers of Pluto, providing the first detailed images of its surface, revealing a landscape of smooth plains, jagged mountains, and evidence of slow-flowing glaciers composed of nitrogen ice. Each pixel of data was meticulously collected, transmitted over many months, and analyzed by teams of scientists, producing a high-resolution map of a world previously seen only as a point of light. Observations included temperature measurements, atmospheric composition, and detection of complex organic molecules, all quietly informing our understanding of distant, icy bodies in the Kuiper Belt. The images captured subtle contrasts in terrain, colors ranging from reddish regions enriched in flins to bright nitrogen plains, and craggy mountain peaks of water ice rising almost 4 kilometers above surrounding plains, features that demonstrate geological processes unfolding over billions of years in a profoundly unhurried manner. A slow reflection on Pluto's orbital relationship with Neptune adds quiet complexity. Despite its occasional crossing of Neptune's orbital path, a 3-to-2 orbital resonance ensures that the two bodies never collide. Pluto completes 2 orbits around the Sun for every 3 of Neptune, a timing that maintains safe separation. This resonance is a subtle gravitational choreography that has persisted for billions of years, providing an almost poetic reminder of the careful balance in the solar system. Even during periods when Pluto is closer to the Sun than Neptune, the resonance guarantees stability, a slow, constant mechanism invisible to the naked eye yet measurable and precise, a celestial safety net woven into the architecture of planetary motion. A soft consideration of rotation, seasons, and axial tilt drifts into focus. Pluto rotates once approximately every 6.39 Earth days, giving rise to long days and nights across its frozen surface. Its axial tilt of 119.6 degrees produces extreme seasons, with poles experiencing decades of continuous sunlight followed by long periods of darkness. These prolonged seasons subtly affect the distribution of ices and atmospheric pressure, inducing slow migrations of nitrogen, methane, and carbon monoxide across the surface. Observations over time reveal shifting frost deposits, faint changes in color, and the gentle sculpting of features such as Sputnik Planitia and surrounding terrains, all unfolding over the course of decades and centuries rather than days or years, emphasizing the quiet patience inherent in Pluto's environment. A soft murmur of scientific detail brings the consideration of surface features and geology. Pluto displays mountains of water ice, plains of nitrogen ice, and regions like Cthulhu Macula, a large dark area enriched in complex organics, flins formed by solar radiation interacting with surface ices. Evidence of tectonic-like activity suggests contraction and expansion of ice layers, the formation of cracks, and the slow movement of glaciers. These processes are gentle, imperceptible in human terms, yet significant over millions of years. The geological diversity, from smooth plains to jagged peaks, creates a delicate balance of contrasts that are visible only through careful observation, each feature a quiet signature of slow, persistent activity on a distant, frozen world. A drifting reflection on observation techniques reminds us that knowledge of Pluto is painstakingly acquired through multiple methods: telescopic photometry, spectroscopy, occultations, and direct spacecraft imaging. Occultations allow the precise measurement of atmospheric pressure and temperature profiles, while spectroscopy reveals composition of ices and trace gases. Light curve analysis helps determine rotation period and shape, particularly before the new horizons encounter refined measurements. Each technique contributes incremental understanding, building a detailed, coherent picture of Pluto over decades of careful, patient work, a slow accumulation of knowledge that mirrors the unhurried motion of the dwarf planet itself. A soft, drifting sense of stillness invites us to contemplate Uranus, the seventh planet from the Sun, quietly circling at an average distance of about 19 astronomical units. Light from our star takes roughly 2 hours and 30 minutes to reach its cloud-shrouded surface, a gentle journey across nearly 3 billion kilometers of silent, frozen space. Uranus travels along a nearly circular orbit, inclined only slightly to the ecliptic, and yet what distinguishes it most profoundly is the tilt of its axis, approximately 97.77 degrees, causing it to rotate almost on its side as it slowly traces its 84-year path around the Sun. This axial orientation produces a unique pattern of seasons, each lasting over 21 Earth years, where poles alternately bask in prolonged sunlight or retreat into decades of quiet darkness, creating subtle cycles of temperature and illumination across the upper atmosphere, a rhythm imperceptible to human perception but measurable through patient observation. A soft curl of thought drifts toward the planet's discovery, a narrative of patient mathematics and observation. In 1781, William Herschel first identified Uranus using a telescope, noticing a faint point of light that appeared different from known stars. Initially thought to be a comet, subsequent measurements revealed its slow movement relative to the background stars, confirming it as a planet. Herschel's careful notes, later verified by astronomers such as Johann Elert Bode, led to Uranus being recognized as the first planet discovered in the modern era, beyond those visible to the unaided eye. This quiet, deliberate discovery expanded our conception of the solar system, a gentle reminder that patient observation can reveal worlds invisible without careful attention, a whisper of knowledge accumulated slowly across nights of precise measurement. A drifting haze of atmosphere draws our attention, for Uranus is shrouded in layers of hydrogen, helium, and methane gas, the latter responsible for its pale cyan hue. The methane absorbs red wavelengths of sunlight, allowing blue and green light to scatter, producing a color that is both muted and steady. Above this, faint clouds of methane ice form subtle, slowly evolving patterns, drifting imperceptibly under the influence of winds that can reach up to 900 kilometers per hour. These winds, though impressive in magnitude, unfold over vast distances with a measured grace, producing faint banding and cloud features that telescope images can detect, yet remain gentle, quiet, and non-dramatic. Uranus lacks the conspicuous storm system seen on Neptune, giving it a subdued, serene appearance that matches the slow, steady motion of its axial tilt and orbital path. A soft ripple of interior structure beckons reflection. Beneath Uranus's cloud layers lies a mantle of water, ammonia, and methane ices surrounding a rocky core, all contributing to its classification as an ice giant. This interior is markedly different from the gas giants Jupiter and Saturn, where hydrogen and helium dominate. The mantle conducts heat less efficiently than the massive envelopes of the gas giants, and Uranus radiates surprisingly little energy into space, emitting only slightly more than it receives from the Sun. This faint internal heat, or lack thereof, contributes to a quiet, subdued convection in the atmosphere, producing minimal storm activity and subtle, slowly moving cloud patterns. The interior structure, layered and largely invisible, underscores the calm, unhurried mechanics that govern the planet's distant existence. A drifting thought of moons and companions brings gentle motion into the narrative. Uranus possesses 27 known moons, each moving in a regular, patient rhythm. The largest, Miranda, Ariel, Umbriel, Titania, and Oberon, exhibit diverse surfaces and geologies, yet all orbit in a generally equatorial plane aligned with Uranus's tilted rotation axis. Miranda, though small, presents remarkable geological diversity, with coronae, vast, gently ridged features, that hint at a history of crustal stretching and internal processes long ceased or slow in pace. Each satellite's orbit, size, and composition offers subtle clues about the planet's formation and evolution, revealing a system in quiet gravitational harmony, where every body contributes to the stability of the whole. Smaller moons, often irregularly shaped, drift along distant orbits, silent companions that rarely draw attention, yet maintain equilibrium in the outer planetary system. A soft consideration of the ring system reveals faint, narrow bands encircling Uranus, first discovered in 1977 through occultation studies. These rings, named for astronomers such as Epsilon, Delta, and Lambda, are composed of dark particles, likely rich in carbon and ranging from micrometers to meters in size. Their positions are stabilized by small shepherd moons, which exert gentle gravitational forces, maintaining the narrow, sharply defined rings against the background of space. Observed through telescopes in the Voyager 2 flyby in 1986, the rings remain calm, subtle features, not visually striking from a distance, yet critical for understanding Uranus's mass distribution, gravitational field, and long-term orbital stability. The ring's muted presence mirrors the quiet elegance of the planet's overall demeanor, providing a soft, consistent feature against the infinite backdrop of the Kuiper belt beyond. A slow, meandering thought on seasonal illumination emerges from Uranus's extreme tilt. During solstices, one pole experiences continuous sunlight while the other remains in darkness, creating subtle temperature gradients and minor circulation patterns in the atmosphere. These prolonged seasonal effects unfold over decades, yet the absence of strong internal heat and subdued winds results in faint changes, almost imperceptible from afar. Observations reveal only subtle shifts in cloud patterns, minor brightness variations, and slight changes in reflectivity, all slowly tracked over time to understand the planet's rhythmic, elongated seasons. The extreme tilt is unique in the solar system, producing conditions both extraordinary and yet quietly persistent, a reminder of the variety of dynamics in planetary systems beyond Earth. A soft ripple of magnetic wonder invites reflection on Uranus's unusual magnetosphere. The field is tilted approximately 59 degrees relative to the rotational axis and offset from the planet's center, creating a highly asymmetric environment. Charged particles follow convoluted paths along magnetic field lines, producing faint auroral glows and ultraviolet wavelengths at high latitudes. Unlike Earth, these auroras are subtle, steady, and spread unevenly, revealing complex interactions between solar wind, planetary rotation, and internal electrical currents. The field itself is likely generated by convection in a layer of ionic water ammonia methane ices, producing a slow, continuous geomagnetic effect. This irregular geometry and gentle magnetic activity remind us that even invisible forces in space exhibit elegance, subtlety, and precise balance. A drifting observation of Voyager 2's encounter in 1986 enriches the narrative with quiet detail. The spacecraft passed within roughly 81,500 kilometers of the cloud tops, capturing imagery of faint cloud bands, subtle storms, and moons previously unseen. Measurements of atmospheric composition revealed hydrogen and helium dominance, with trace methane forming the pale blue coloration. Temperature profiles showed very low upper atmospheric temperatures, averaging around 53 kelvins, while the interior maintained modest heat. Data from this brief passage required careful analysis over years, yielding a patient accumulation of knowledge that transformed a distant point of light into a richly characterized world, a slow unveiling of planetary truth with every byte of information transmitted across billions of kilometers of space. A soft meditation on rotational dynamics emphasizes Uranus's 16.5-hour rotation period. This relatively rapid spin contributes to equatorial bulging, producing a subtle flattening at the poles and a gently elongated equatorial circumference. Combined with the extreme axial tilt, this rotation shapes the trajectories of moons, rings, and atmospheric motions in ways that are almost imperceptible yet profoundly precise. The interplay of rotation, tilt, and internal mass distribution exemplifies the slow, intricate balancing act of physics, where every factor influences the system over millennia, producing an enduring and stable planetary configuration. A soft reflection on thermal behavior emerges, as Uranus emits only slightly more energy than it receives from the Sun, in stark contrast to Neptune. The low heat flux results in subdued convection, quiet winds, and a relative absence of strong storm systems. Subtle variations in cloud opacity and methane concentrations lead to gentle banding and minor changes in brightness, measured carefully by telescopes over decades. The faint thermal energy from internal sources and the modest sunlight combine to create a tranquil, unhurried planetary environment, a world where energetic displays are muted, and activity is gentle, predictable, and slow-moving. A drifting thought of Moon's surface features brings Miranda back into focus. Its coronae, grooved and ridged expanses, suggest episodes of past geological activity, possibly triggered by tidal interactions with Uranus. Aerial and umbreal display contrasting surface compositions, with aerial exhibiting evidence of past resurfacing and younger ice, while umbreal appears darker and more heavily cratered, bearing witness to ancient impacts and long-term stability. Titania and Oberon, larger and more distant, present faint evidence of past tectonic and impact processes, subtle reminders of slow, patient forces sculpting their surfaces. These satellites, orbiting a tilted, gently rotating planet, contribute to a slow celestial rhythm, each motion precise and unhurried, reinforcing the calm equilibrium of the Uranian system. Drifting gently through thought, we consider Saturn, the sixth planet from the Sun, quietly orbiting at an average distance of about 9.5 astronomical units. At this separation, sunlight takes approximately 1 hour and 19 minutes to reach its clouded surface, traveling across roughly 1.43 billion kilometers in perfect silence. Saturn's orbit is a nearly circular ellipse, inclined by a mere 2.49 degrees relative to the ecliptic, allowing it to maintain a steady, unhurried path through the solar system. Its rotation is swift for its immense size, completing a rotation in approximately 10 hours and 39 minutes, a pace that produces a noticeable equatorial bulge, subtly flattening the poles. This rapid spin and flattened shape are gentle reminders of the interplay between gravity and centrifugal forces, creating a soft, steady rhythm in the planet's structure that persists over countless rotations without any interruption or disturbance. Floating slowly into memory, Saturn's discovery invites reflection, though it is a planet known since ancient times. Observed by naked eye from Earth, it has been quietly noted in the skies of Mesopotamia, Babylonia, and Greece for millennia. The earliest records, etched on clay tablets, describe its motion among the stars with careful attention, tracking slow changes night after night. It was not until the invention of telescopes that more detailed observation became possible, revealing the planet's faint, extraordinary ring system. Galileo Galilei first observed these rings in 1610, though they appeared as ears due to telescope limitations, and Christian Huygens later correctly interpreted them as a disc-like structure surrounding the planet. The discovery of rings was a patient unfolding of knowledge, each careful observation adding to a gradual understanding of Saturn's serene grandeur. Lingering in the mind, Saturn's atmosphere drifts into focus, cloaked in layers of hydrogen and helium, with minor traces of methane, ammonia, and water vapor. These gases form bands that run parallel to its equator, subtly shading the planet in muted gold, pale yellow, and gentle brown tones, unlike the vivid contrasts seen on Jupiter. Winds in the upper atmosphere reach up to 1,800 km per hour at the equator, flowing in smooth, continuous belts that form long-lived hexagonal patterns at the North Pole and more diffuse, swirling zones elsewhere. Despite these high speeds, the scale of the planet and the depth of its gaseous layers produce motions that are calm and predictable on a cosmic scale, moving with the quiet elegance of a slowly turning carousel, a spectacle measured by patient instruments rather than felt in any sudden or alarming way. Drifting deeper, thoughts settle on Saturn's internal structure, revealing layers that are both immense and unhurried. Beneath the outer hydrogen-helium envelope lies a fluid metallic hydrogen layer, where pressure is immense yet constant, flowing slowly and producing a gentle magnetic dynamo. Deeper still, a core composed of rock, metals, and ices resides, weighing in at roughly 15 Earth masses, and supporting the planet's overall gravitational pull with silent constancy. Internal heat generated by slow contraction, known as Kelvin-Helmholtz contraction, radiates outward in small, steady amounts, powering subtle convection in the outer layers. These processes unfold over millions of years, invisible to casual observation, producing gentle variations in atmospheric patterns that form without haste, without sudden shifts, a quiet testimony to the calm precision of planetary physics. Turning attention gently outward, Saturn's moons drift into thought, over 80 known companions moving in quiet, predictable paths. Titan, the largest, is remarkable, with a thick nitrogen atmosphere, hydrocarbon lakes, and slowly moving dunes of dark, organic-rich material. Its atmosphere, denser than Earth's, drifts with winds of only a few tens of kilometers per hour, producing long-term changes in weather patterns that are slow and gradual, observed patiently over years. Enceladus, another notable moon, exhibits icy plumes from fissures near its south pole, ejecting water and organic compounds into space in a quiet, measured rhythm, contributing material to Saturn's E-ring. Other moons, smaller and more distant, maintain their positions through subtle gravitational interactions, forming a harmonious system that unfolds with patient precision, almost as if choreographed to the slow heartbeat of the planet itself. Reflecting softly, Saturn's ring system invites a sense of delicate awe, though without excitement, for it is composed of countless icy particles, ranging from micrometers to meters in size, each orbiting in precise, narrow bands. Named for astronomers such as A, B, C, D, E, F, and G, these rings vary in density, thickness, and composition, reflecting light to produce a gentle, luminous shimmer that is detectable even through modest telescopes. Shepherd moons exert small gravitational tugs on ring particles, maintaining gaps and preventing dispersal, producing subtle structures such as the Cassini division. The ring's quiet persistence over millions of years offers a reminder of enduring stability, a slow-motion ballet in which countless particles trace invisible paths in perfect unison, each in its own measured orbit, unhurried and unobtrusive. Gently turning inward, Saturn's magnetosphere unfolds in thought, an expansive region dominated by a magnetic field generated by the motion of metallic hydrogen in its interior. Tilted by approximately 0.06 degrees relative to its rotational axis and aligned almost perfectly, the magnetic field traps charged particles, producing auroras at high latitudes. These auroras are faint, glowing in ultraviolet and infrared wavelengths, dancing slowly across polar regions with minimal variation over time. Interactions with the solar wind and material from Enceladus plumes create gentle currents and subtle distortions, all unfolding quietly, far from human perception, yet measurable with patient instruments. The magnetosphere extends millions of kilometers, a calm, protective envelope that traces the rhythms of internal and external forces in slow harmony. Floating backward into memory, the Cassini-Huygens mission drifts into thought, arriving at Saturn in 2004 and spending 13 years collecting data with patient dedication. Cassini mapped atmospheric composition, measured gravity, imaged moons and rings, and observed seasonal changes over a third of the planet's orbit. The Huygens probe descended to Titan in 2005, transmitting images and data that revealed surface lakes of methane and ethane, river channels, and a dense haze, all at a leisurely pace over hours of descent. Each measurement, pixel, and spectrum was carefully analyzed by scientists over months and years, transforming Saturn from a distant point of light into a richly detailed system, observed not in a single glance but through patient accumulation of quiet, exacting knowledge. Turning attention gently to rotation and obliqueness, Saturn spins rapidly, creating an equatorial diameter significantly larger than the polar diameter. This flattening, combined with differential rotation of cloud layers, subtly affects the motion of rings and moons, producing gentle equatorial bulges and slight latitudinal variations. Winds in the equatorial region reach maximum speeds, while polar regions rotate more slowly, a rhythm that is both stable and slowly evolving over time. These physical characteristics, measured with telescopes and spacecraft instruments, unfold imperceptibly, a slow symphony of motion and gravity orchestrated over eons without interruption, a quiet testament to the planet's persistent equilibrium. A gentle meander of thought moves toward thermal characteristics. Saturn radiates approximately 2.3 times more energy than it receives from the Sun, a gentle excess powered by slow gravitational contraction and settling of helium droplets through the metallic hydrogen layer. This energy warms the planet subtly, driving modest convection in the upper atmosphere and maintaining the delicate belts, zones, and occasional storms visible from afar. Unlike Jupiter, Saturn's internal energy is lower, producing gentler weather systems, soft and meandering, devoid of extreme or violent activity, measured in gradual changes across decades. Wandering slowly through seasonal cycles, Saturn's axial tilt of about 26.73 degrees produces long summers and winters for each hemisphere, with sunlight gradually shifting across latitudes over 29.5 Earth years. Atmospheric phenomena, cloud patterns, and subtle color variations respond slowly to these changes, providing observers with long-term insights into planetary climatology. The prolonged seasons unfold almost imperceptibly, emphasizing patience and continuity in planetary behavior, with variations measured over years rather than days. A quiet ripple of thought turns toward minor moons and distant satellites, which interact with rings and larger moons in delicate gravitational balance. These bodies, irregular in shape and orbit, contribute to the stability of rings, forming gaps, waves, and small arcs, each movement imperceptible yet precise. Even tiny moons like Pan and Daphnis maintain narrow gaps within rings, shepherding particles with gentle gravitational nudges. Their roles, subtle and largely unseen, create a quiet harmony in the Saturnian system, each action unfolding with perfect timing over centuries of motion. A quiet hush seems to settle around our thoughts as we turn gently toward Jupiter, the largest planet in our solar system, slowly orbiting at an average distance of about 5.2 astronomical units from the Sun. At this distance, sunlight takes just over 43 minutes to drift across space and reach the uppermost layers of its dense atmosphere, a journey spanning roughly 778 million kilometers in absolute silence. Jupiter's orbit is only slightly elliptical, allowing it to glide in a nearly consistent, predictable path around our star, while its massive size ensures a strong gravitational presence that shapes the orbits of numerous moons, asteroids, and even influences the asteroid belt between Mars and itself. Its rapid rotation, completing a full turn in just under 10 hours, stretches the planet slightly at the equator, giving it a gentle oblate shape, like a soft balloon that has been pressed just enough to create a subtle, perpetual bulge. This motion, while immense in scale, is entirely patient and consistent, a rhythmic rotation maintained for billions of years. Floating slowly in contemplation, one considers the long history of human observation of Jupiter. Known since antiquity, it was documented by Babylonian astronomers over 2 millennia ago, who tracked its movement meticulously against the backdrop of fixed stars. These early records captured the slow progression of Jupiter across the sky, noting retrograde motions and positions at specific times of year. The invention of the telescope transformed our understanding in 1610, when Galileo Galilei discovered its four largest moons, later called the Galilean satellites, Io, Europa, Ganymede, and Callisto. These moons, orbiting in predictable, serene patterns, revealed that not all celestial bodies revolve around Earth, a quiet revolution in understanding that unfolded gradually, without haste, reshaping astronomy in the most measured way. A drifting awareness of Jupiter's atmosphere brings attention to the swirling bands and zones that gently wrap the planet in alternating belts of clouds composed primarily of hydrogen and helium, with subtle admixtures of ammonia, methane, water vapor, and other trace gases. These bands are colored in soft hues of white, beige, pale orange, and gentle brown, flowing in continuous currents that move at different velocities depending on latitude. Winds in some regions reach speeds exceeding 600 kilometers per hour, yet in the scale of Jupiter's immense circumference, these are slow, methodical flows, creating long-lived structures such as the Great Red Spot, a storm larger than Earth itself, which has persisted for at least 3 centuries. Its slow rotation and gradual evolution are measured in decades and centuries rather than days or months, a patient display of atmospheric dynamics that changes almost imperceptibly over human lifetimes. Gently, one drifts into consideration of the interior of this massive gas giant. Beneath the upper cloud layers lies a region of molecular hydrogen, which gradually transitions into metallic hydrogen under immense pressure, a substance that flows slowly, conducting electricity and creating Jupiter's powerful magnetic field. Deeper still, the core is thought to be composed of rock and ice, weighing roughly 10 to 20 Earth masses, quietly anchoring the immense gaseous envelope above it. Heat from the interior radiates outward, partially due to slow gravitational contraction, providing energy that subtly influences atmospheric convection. This process is unhurried, unfolding over millions of years, producing gentle rises and falls in temperature and pressure that shape the complex cloud structures without abrupt interruption or sudden changes. Turning attentively to Jupiter's moons, one notices a symphony of companionship unfolding with extreme patience. The 4 Galilean moons follow consistent, almost mechanical orbits, while dozens of smaller satellites drift at more distant and irregular paths. Io, volcanically active, emits sulfurous plumes and lava flows in gentle, recurring cycles, producing faint modifications to Jupiter's magnetosphere. Europa, beneath its icy crust, harbors an ocean of liquid water, with tides induced by Jupiter's gravity, moving slowly and predictably, potentially influencing the chemistry of the subsurface seas. Ganymede, the largest moon in the solar system, possesses its own magnetic field, interacting softly with Jupiter's, while Callisto bears countless impact craters, the record of ancient collisions preserved in quiet stillness. Each moon contributes to the gravitational harmony of the Jovian system, performing an invisible dance that unfolds over hours, days, and centuries, entirely orderly and serene. A delicate current of thought drifts toward Jupiter's ring system, almost imperceptible compared to Saturn's grandeur. Composed mainly of dust particles ejected from small inner moons, the rings are faint and diffuse, orbiting in carefully measured lanes. Although they reflect little sunlight, they persist as subtle markers of past impacts and steady orbital mechanics. Small shepherd moons and the continual motion of particles maintain their shape and boundaries, creating a quiet, almost imperceptible system of order, where the slow accumulation of impacts and the patient forces of gravity interact to produce a serene, enduring feature. Considering the magnetic environment of Jupiter produces a sense of quiet wonder, though devoid of excitement. Its magnetic field is enormous, extending millions of kilometers into space, strong enough to trap charged particles and generate auroras at the poles. These auroras glow in ultraviolet and infrared light, appearing as faint curtains slowly shifting in response to solar wind and volcanic emissions from Io. The patterns evolve gradually, over hours and days, without sudden bursts or flashes visible to the naked eye, representing a calm, steady interaction between the planet, its moons, and the Sun, measured by instruments rather than perceived by casual observation. Turning inward, the thermal characteristics of Jupiter reveal gentle contrasts between absorbed solar energy and internal heat. The planet radiates approximately 1.6 times as much energy as it receives from the Sun, a slow, quiet contribution from contraction and residual heat from formation billions of years ago. This energy drives subtle atmospheric motions, feeding storms and the slowly changing cloud bands. The internal heat is modest relative to the planet's size, creating movements and circulations that are steady and predictable, without sudden surges or violent disruption, an example of the measured patience inherent in planetary processes. Softly considering the rotation and obliqueness of Jupiter, one notes how the planet's rapid spin, completing a rotation in less than 10 hours, produces an equatorial diameter larger than the polar diameter by nearly 10%. This shape influences atmospheric flows, subtly modifying wind speeds at different latitudes and contributing to the stability of zonal bands. Observations over decades reveal only gradual changes, emphasizing the slow, deliberate rhythms of Jovian dynamics, where immense forces are balanced precisely over vast timescales. Drifting gently toward Jupiter's historical exploration, the Voyager missions in the late 1970s, followed by Galileo in the 1990s and Juno more recently, provided patient accumulation of knowledge. Each spacecraft collected images, spectra, and gravitational measurements that slowly revealed details of atmosphere, magnetic field, internal structure, rings, and moons. Juno's polar orbits, completed over multiple years, allow precise measurements of gravitational variations, revealing subtle density distributions, wind depth, and internal structure. Each observation adds another small, quiet piece to the understanding of this giant, achieved only through persistent, meticulous effort rather than instantaneous revelation. A soft, lingering reflection turns toward Jupiter's complex weather patterns. Long-lived storms, including the Great Red Spot and smaller ovals, drift slowly across latitudes, interacting minimally with adjacent bands but contributing to gradual mixing of atmospheric material. Lightning flashes in deeper clouds occur with low frequency, unnoticed by distant observers, producing minor chemical effects without observable sudden change. Seasonal variations are minimal due to Jupiter's small axial tilt of 3.13 degrees, meaning the atmospheric circulation remains largely steady, a persistent, unhurried system of zonal winds, eddies, and vortices measured over decades. Considering Jupiter's faint thermal emission, infrared observations reveal subtle heat escaping from the interior, driving mild convection and feeding atmospheric turbulence. Bands of rising and falling gas extend thousands of kilometers, flowing at different velocities, yet the flows remain steady, like a calm river with gentle eddies, invisible to direct perception but measurable by patient instruments. These processes unfold over long timescales, a quiet orchestration of energy, gravity, and rotation, imperceptible to most observers but central to the planet's continued stability. Finally drifting toward its interactions with the Solar System, Jupiter's immense gravity influences asteroid paths, comet trajectories, and the stability of the asteroid belt. Its Lagrange points, stable regions of gravitational equilibrium, host Trojan asteroids in quiet co-orbital motion, gently accompanying the planet around the Sun. These small bodies drift slowly, their paths shaped by the subtle pull of Jupiter's mass, unhurried and unremarkable to anyone watching from afar, yet precisely predictable through celestial mechanics. A gentle hush seems to settle over the mind as we consider Ceres, quietly drifting in the asteroid belt between Mars and Jupiter at an average distance of approximately 2.8 astronomical units from the Sun. At this separation, sunlight takes nearly 23 minutes to reach its surface, traveling across roughly 419 million kilometers in complete silence, unaccompanied by sound or haste. Ceres follows a slightly elliptical orbit, inclined by only 10.6 degrees relative to the ecliptic, tracing a patient path among countless smaller asteroids and debris, a slow-motion ballet that has persisted for billions of years. Its rotation period is just under 9 hours, producing modest day-night cycles across a surface composed of rock, clay, and ice, materials that tell a quiet story of gradual formation, accretion, and the patient shaping forces of gravity and solar radiation. Drifting softly into memory, one recalls Ceres' discovery by Giuseppe Piazzi in 1801, a meticulous observation in Palermo, Sicily. It was initially considered a planet, a solitary dot moving against the starry sky, but as more objects in the same region were identified, astronomers recognized the need for a new classification. This patient process of observation and categorization unfolded slowly, allowing the human mind to adjust to the notion that the solar system contains a belt of numerous small bodies, each quietly orbiting the Sun, yet each contributing to the structure of the inner solar system. Over time, Ceres was reclassified as a dwarf planet in 2006, acknowledging its sufficient mass to maintain hydrostatic equilibrium while recognizing the vast population of neighboring asteroids that share its orbital space. A soft current of thought drifts toward the surface of Ceres, which is a mixture of hydrated silicates, carbonates, and water ice. The surface bears numerous craters, formed over billions of years by impacts from smaller asteroids and meteoroids, each one a gentle indentation marking quiet, slow interactions with the surrounding space. Some craters, such as a crater, reveal bright spots, now known to be deposits of sodium carbonate, subtly reflecting sunlight like small, icy jewels scattered across the landscape. These bright regions are composed of salts left behind by briny water that seep to the surface and evaporated in the thin exosphere, a process occurring over millions of years, entirely imperceptible on human timescales. The surface also exhibits gentle ridges and fractures, evidence of internal stresses and slow expansion or contraction, whispering the history of a world shaped in quiet patience. Floating more deeply, one can consider Ceres' potential internal structure, which is believed to include a differentiated core and mantle. The core is thought to be primarily rocky, composed of silicates and metals, providing a firm foundation for the overlying layers. Above this, a mantle rich in water ice may exist, perhaps even forming a subsurface ocean beneath a few tens of kilometers of rock and ice. This hidden ocean, if it exists, interacts subtly with the crust, creating fractures and potentially contributing to localized cryovolcanism, such as that observed in the Ahuna Mons region. These slow geological processes unfold over millions or billions of years, a quiet, persistent shaping of a dwarf planet that is almost invisible to casual observation, yet profoundly significant for understanding planetary evolution. A soft ripple of thought turns toward Ceres' rotation and its modest shape. Unlike highly oblate gas giants, Ceres is nearly spherical, with only slight flattening at the poles, a gentle reminder of the balance between gravitational forces and its modest spin of roughly 9 hours. The axial tilt is small, estimated at around 4 degrees, producing very gradual seasonal variations across its surface. Solar heating is weak at this distance, yet over long periods it drives sublimation of surface ice, contributing to the subtle evolution of bright spots and localized surface changes, a process slow and patient, observed carefully through spacecraft imagery and spectral analysis. Drifting attentively, one considers the Dawn spacecraft, which arrived at Ceres in 2015 after years of silent travel through the solar system. Dawn orbited the dwarf planet for more than 3 years, collecting detailed images, gravity measurements, and compositional data. These observations revealed topographic features, bright salt deposits, and subtle evidence of past internal activity, each measurement accumulating slowly into a coherent understanding of Ceres as more than a mere dot among asteroids. Instruments recorded data that would take scientists months and years to analyze, translating faint signals into maps of elevation, gravity, and chemical composition, all at a pace that mirrors the leisurely evolution of the world itself. Floating toward the moons and neighboring asteroids, one recalls that Ceres has no known natural satellites, moving alone in a vast population of smaller bodies in the asteroid belt. Its gravitational influence is sufficient to maintain its own hydrostatic equilibrium, yet it shares space with hundreds of thousands of other asteroids, all tracing slow, interwoven paths. Some near-resonant orbits with Jupiter subtly shape the overall distribution of the belt, creating gaps in regions of relative stability, patterns discernible only over centuries and millennia of patient observation. The interactions are almost imperceptible, a cosmic dance in which timing and distance are everything, yet motion is so slow that the eye would perceive nothing at all. A soft drift of consideration turns to the thermal properties of Ceres. The dwarf planet absorbs modest amounts of sunlight and radiates heat slowly, maintaining surface temperatures typically between -105 and -38 degrees Celsius, depending on latitude and solar incidence. Subsurface ice remains stable over millions of years, insulated by a layer of regolith, while occasional localized heating from radioactive decay or past cryovolcanic activity contributes minutely to interior dynamics. Thermal inertia is low, meaning the surface responds slowly to changes in sunlight, emphasizing the patient rhythm of heating and cooling that has persisted since Ceres formation. Gently turning attention to composition, one notes that Ceres contains significant carbonates, hydrated clays, and traces of ammonium-bearing minerals. These substances form from slow aqueous processes that likely occurred early in the planet's history, when liquid water may have been more abundant beneath the surface. Chemical interactions between water, salts, and rock have left subtle fingerprints across the crust, visible today as spectral variations and bright deposits within craters. Even small variations in concentration produce detectable differences in reflectance, yet the process remains exceedingly gradual, unhurried, and nearly imperceptible from orbit, a quiet narrative etched into stone and ice. A soft awareness drifts toward Ceres' gravitational field, which is modest yet measurable, allowing precise calculation of mass and density. Its average density of about 2.16 grams per cubic centimeter suggests a significant proportion of water ice beneath a rocky crust, a combination that supports hydrostatic equilibrium. Variations in gravity across the surface indicate subtle mass concentrations, perhaps related to ancient cryovolcanic domes, buried ice deposits, or differentiated layers, revealing how even small deviations in mass unfold slowly into detectable patterns under patient observation. Flowing onward in thought, one contemplates Ceres' place in the solar system. Its orbit lies within the main asteroid belt, yet its composition, size, and hydrostatic equilibrium distinguish it from smaller asteroids. It represents a bridge between the rocky worlds of the inner solar system and the icy, volatile-rich bodies of the outer system, a quiet intermediary that has persisted for over 4 billion years. The interactions of Ceres with neighboring bodies, through gravitational nudges and resonances, shape the belt's overall structure, yet all these motions occur with extreme patience, measured over centuries rather than moments, revealing the cosmic choreography in gentle, imperceptible increments. A soft reflection turns to the study of bright spots on Ceres, particularly those in a crater. These areas, composed mainly of sodium carbonate and other salts, suggest slow, episodic eruptions of briny water from below the surface. The water sublimates quickly in the low-pressure environment, leaving behind reflective deposits that may slowly diffuse or darken over time. These features are remarkable not for their drama, but for the patient chemical and geological processes they represent, unfolding over millions of years in silence, a quiet testimony to the subtlety of planetary evolution. Drifting now to the thought of potential habitability, Ceres offers a gentle hint of the possibility that small, icy bodies may host environments conducive to chemistry that could support life, at least in a microscopic sense. If subsurface water exists in pockets or a global ocean, it may slowly interact with minerals and salts, producing chemical gradients. These gradients unfold over vast time scales, utterly invisible to human perception, yet measurable through spectral analysis, modeling, and laboratory simulation. The process is quiet, slow, and meticulous, entirely in keeping with the patient, serene nature of the dwarf planet itself. A soft turn toward Ceres observation from Earth reveals the gradual accumulation of knowledge through telescopic imaging and spectral studies. Observers noticed subtle variations in brightness as the planet rotated, hinting at surface heterogeneity. Repeated observations over months and years allowed astronomers to map features, identify bright spots, and estimate rotation period. Each measurement, tiny and incremental, contributes to a slowly growing understanding, illustrating how patient observation, over decades, gradually transforms distant points of light into tangible, richly characterized worlds. Floating in the quiet of imagination, one might consider Ceres' connection to meteorites on Earth. Certain carbonaceous chondrites are believed to originate from Ceres-like bodies, carrying hydrated minerals and organic compounds across millions of kilometers to our planet. These fragments drift slowly through space, their journey spanning millions of years, before eventual encounter with Earth's atmosphere. Such connections are subtle, almost imperceptible, yet they allow scientists to study the chemistry and history of distant worlds without ever leaving our own, a gentle, measured bridge across space and time. Drifting lastly toward the broader role of Ceres in planetary science, one notes that it serves as a laboratory for understanding differentiation, aqueous alteration, and hydrothermal processes on small bodies. Its surface and interior hold clues about the early solar system, revealing slow interactions between rock, water, and heat. Every crater, ridge, and bright spot tells a quiet story of gradual evolution, patiently recorded over billions of years. Through study and observation, Ceres exemplifies the beauty of unhurried planetary processes, offering insights that unfold ever so slowly, a gentle testament to the serenity and precision inherent in the cosmos. A gentle warmth settles over our thoughts as we drift toward Mars, the fourth planet from the Sun, quietly orbiting at an average distance of approximately 1.5 astronomical units. At this range, sunlight requires roughly 12.5 minutes to traverse the 228 million kilometers to reach the ruddy surface, a soft reminder of the vast emptiness that separates worlds. Mars follows an elliptical orbit with a modest eccentricity of 0.093, inclined by about 1.85 degrees relative to the ecliptic, producing a slow, predictable path that has persisted for over 4 billion years. Its rotation period, slightly longer than Earth's at 24 hours and 37 minutes, creates gentle day-night cycles, while subtle variations in axial tilt, currently around 25.2 degrees, give rise to slowly changing seasons that unfold over nearly twice the length of our familiar earthly cycles. The interplay of orbit, tilt, and rotation produces a calm, unhurried rhythm on a planet both familiar and distant. In the quiet corridors of history, Mars drifts into human observation, its reddish hue noted on clay tablets and stone carvings since prehistory. Ancient civilizations, from the Babylonians to the Egyptians, assigned it symbolic significance, often relating its color to blood, war, or vitality, though these interpretations were tentative, shaped by curiosity and human imagination. Telescopic observations beginning in the 17th century revealed polar caps, subtle surface markings, and shifting brightness, slowly transforming Mars from a mere dot of color into a world with discernible features. Careful measurement of its retrograde motion and changes in brightness led to understanding its orbit with ever-increasing precision, an exercise in patience and meticulous calculation stretching across centuries of human endeavor. A quiet reverie brings the Martian surface to attention, a landscape of iron-rich dust and rock, giving the planet its characteristic reddish appearance. Vast plains, such as Arabia Terra and Elysium Planitia, stretch beneath a thin, carbon dioxide-rich atmosphere, while towering volcanoes like Olympus Mons rise slowly, almost imperceptibly, over millions of years, the largest known in the solar system. Deep canyons such as Valles Mar and Eris extend for thousands of kilometers, carved by processes that unfolded in the distant past, leaving subtle records of tectonic activity and erosion. Each crater, fissure, and ridge carries with it a narrative of cosmic impacts and gradual surface evolution, observed and measured patiently by orbiters, landers, and rovers with instruments designed to capture every gentle variation in terrain, reflectivity, and composition. A drifting curiosity carries attention to the atmosphere of Mars, a tenuous envelope composed primarily of carbon dioxide, with minor amounts of nitrogen, argon, oxygen, and traces of water vapor. This fragile layer, only about 0.6% of Earth's atmospheric pressure, supports wind patterns that sweep dust across the surface, forming dunes and ripples that shift imperceptibly over months and years. Seasonal sublimation of polar carbon dioxide ice drives gentle circulations, creating predictable changes that scientists monitor with patience over multiple Martian years. Dust storms, though occasionally planet-wide, unfold gradually and dissipate slowly, illustrating that Martian weather is measured in persistence rather than immediacy, observed through instruments with meticulous care rather than experienced directly by human senses. Gentle musings drift toward water, a subject that has long intrigued scientists and dreamers alike. Though liquid water is not stable on the surface under present conditions, evidence of ancient rivers, deltas, and lake beds suggests a past environment of slow, flowing water. Polar ice caps, composed primarily of water ice with a seasonal layer of carbon dioxide, expand and contract with quiet precision throughout the Martian year. Subsurface ice deposits persist even at lower latitudes, interacting subtly with soil and dust to form hydrated minerals, salts, and frost features, all unfolding over geological timescales, shaping the landscape in imperceptible but persistent ways. Turning thoughts toward Mars' moons, Phobos and Deimos drift into attention, tiny, irregular companions that orbit with quiet diligence. Phobos, the larger, completes an orbit in just over 7 hours, slowly spiraling inward under tidal forces that may eventually bring it close enough to break apart. Deimos, farther out, circles the planet every 30.3 hours in a more sedate path, exhibiting minimal perturbation. Likely captured asteroids from the nearby belt, these moons interact subtly with Mars' gravity, casting shifting shadows across the surface with patient consistency, marking time on scales imperceptible to human experience yet meticulously observed by orbiting instruments. Reflections wander to exploration, beginning with the Mariner missions of the 1960s and 1970s, which first imaged the surface through slow, precise orbital passes. Viking landers in the mid-1970s analyzed soil chemistry and meteorological patterns over extended periods, providing patient datasets that continue to inform understanding. More recent missions, including Mars Global Surveyor, Mars Odyssey, and the Mars Reconnaissance Orbiter, have accumulated years of imaging and compositional information, building a meticulous picture of the surface and subsurface. Rovers such as Spirit, Opportunity, Curiosity, and Perseverance traverse the landscape at deliberate paces, collecting rocks, analyzing soil, and even producing tiny oxygen samples, each experiment unfolding slowly, like a quiet diary written in stone and dust. A wandering thought drifts toward Martian geology, revealing layers of sedimentary rock, volcanic plains, and impact basins. Tharsis and Elysium volcanic regions rise gently, evidence of tectonic uplift and volcanic activity over eons. Sedimentary deposits, sometimes enriched in clay minerals or sulfates, suggest long-term interactions with water, while craters of varying size mark meteoric bombardment across billions of years. Each impact, lava flow, and erosional event adds to the subtle layering of the landscape, a patient testament to the slow unfolding of planetary history. Attention turns to chemical composition, revealing basaltic rocks, iron oxides, and other silicate minerals that quietly record the planet's history. Ferric iron imparts the familiar red hue, while other oxides contribute subtle variations in color and reflectivity. Regolith grains hold evidence of wind transport, impact comminution, and minimal water interactions, a patient record of processes unfolding over eons. Analytical instruments on rovers and orbiters measure spectral signatures with meticulous accuracy, translating tiny variations into composition maps that grow richer with each passing year. Consideration drifts toward past climate, a long story written in valleys, deltas, and mineral deposits. Billions of years ago, Mars may have held a denser atmosphere capable of sustaining liquid water on the surface. Obliquity variations, volcanic outgassing, and slow geological shifts influenced temperature, ice stability, and dust deposition over millions of years, narratives only appreciable over vast timescales and imperceptible to casual observation, yet profoundly recorded in the landscape. Thoughts wander toward the possibility of life, or at least habitable conditions, a subject that unfolds with patient curiosity. Subsurface ice, ancient hydrated minerals, and seasonal methane detections provide faint clues, none dramatic on human scales, but cumulatively suggesting that chemistry capable of sustaining microbial life may have quietly persisted in niches. Instruments on orbiters and rovers detect these subtle signals, and laboratory simulations explore slow chemical interactions, patience being the essential tool in revealing understated truths. The drifting focus turns to Mars' magnetic history, where local crustal fields hint at an ancient dynamo that ceased billions of years ago. These residual magnetic patches interact subtly with the solar wind, producing localized auroral phenomena, faint and almost imperceptible to casual observation. They serve as quiet reminders that planetary processes can continue to leave traces long after active forces have passed, each anomaly a whisper from deep time. Contemplating seasonal cycles, dust storms, sublimation of polar ice, and minor atmospheric shifts unfold with consistent patience. Frost moves, albedo changes gradually, and dust redistributes slowly, creating a planetary rhythm both continuous and imperceptible, a quiet breathing of Mars observed only by instruments designed for long-term patience. Subtle reflections turn toward gravity and atmospheric escape. Mars' lower gravity, around 38% of Earth's, permits particles in the upper atmosphere to drift slowly into space. Hydrogen and helium escape gradually, while heavier gases linger longer, shaping climate, surface chemistry, and habitability over millions or billions of years, nearly imperceptible on human timescales yet vital to planetary evolution. A meandering thought drifts toward impact history. Craters cover much of the surface, from small indentations to enormous basins like Hellas, extending thousands of kilometers. Impacts redistribute material, expose subsurface ice, and generate localized heating, unfolding silently across vast spans of time. Each collision is a quiet punctuation in the ongoing narrative of the planet. Modern exploration technology draws attention, orbiters probing subsurface ice layers with radar, spectral sensors mapping minerals, and high-resolution cameras tracking subtle changes. Rovers move meters per sol, instruments collecting hundreds of data points per hour, forming a slowly accumulating understanding of Mars, patience the primary tool in uncovering the planet's secrets, both literal and figurative. A gentle, grounding presence drifts into thought as we turn our attention to Earth, the third planet from the Sun, orbiting at an average distance of roughly 1 astronomical unit, or about 150 million kilometers. Sunlight travels this distance in just over 8 minutes, carrying warmth and light across the void to reach oceans, continents, and skies, a steady rhythm that has persisted for billions of years. Earth's orbit is nearly circular, with an eccentricity of 0.0167, and its axis tilts at 23.44 degrees, producing seasons that wax and wane with a graceful, predictable cadence. Rotation occurs once every 23 hours, 56 minutes, and 4 seconds, creating day and night cycles so familiar they pass unnoticed, yet their consistency forms the heartbeat of planetary time. Memories of early observation drift gently, recalling that humans have gazed at Earth from within it for as long as consciousness has allowed. Ancient civilizations mapped coastlines, noted solar and lunar cycles, and recorded eclipses, slowly understanding the motions of celestial neighbors in relation to their home. Earth's roundness was intuited by philosophers, calculated by early astronomers, and eventually confirmed by measurements and exploration, a patient accumulation of knowledge that turned observation into understanding. The advent of space travel brought a new perspective, literally stepping beyond our atmosphere to see the planet as a pale blue dot, a fragile jewel suspended in silent darkness. A quiet reflection turns to the planet's structure, a layered assembly of crust, mantle, and core. The thin lithosphere supports oceans and continents, floating atop slowly convecting mantle rock that moves at rates of mere centimeters per year. The outer core of molten iron and nickel circulates, generating Earth's magnetic field, while the solid inner core slowly rotates and grows over geological time. These internal motions unfold with patient precision, invisible to daily experience yet essential to maintaining a stable climate, magnetic shield, and tectonic activity that continuously reshapes the surface in imperceptible increments. The oceans emerge softly into awareness, vast reservoirs of water covering roughly 71% of Earth's surface. Their depths vary, from shallow coastal shelves to trenches exceeding 11 kilometers, the Mariana Trench being the deepest. Ocean currents move with patient slowness, distributing heat, nutrients, and salinity across the globe, influencing climate and ecosystems in a quiet, interconnected network. Waves break along shores, tides rise and fall under lunar influence, and subtle changes in temperature and chemistry ripple across time, shaping life in ways invisible to the casual observer but profound in scope. Turning gently to the atmosphere, one notices layers of nitrogen, oxygen, argon, carbon dioxide, and trace gases forming a protective envelope. Troposphere, stratosphere, mesosphere, thermosphere, and exosphere interact subtly with incoming solar radiation, guiding weather, distributing heat, and sheltering life from cosmic and ultraviolet rays. Convection, pressure systems, and wind currents all operate over gradual scales, producing patterns of clouds, precipitation, and seasonal change, recorded patiently by instruments that track the delicate balance sustaining the biosphere. A calm, meandering thought drifts toward Earth's biosphere, a network of life both abundant and intricate. Plants, animals, fungi, and microorganisms engage in cycles of growth, decay, and reproduction, each process unfolding slowly yet persistently. Photosynthesis captures sunlight, storing energy in chemical bonds, while respiration and decomposition return it to the atmosphere. Nutrient cycles of carbon, nitrogen, phosphorus, and water flow continuously but gently, sustaining ecosystems that are both resilient and fragile, an unhurried balance maintained over millions of years of evolution. Geological time drifts into consideration, revealing continents that drift at mere centimeters per year, mountains that rise and erode, and volcanic activity that slowly shapes the surface. Earthquakes release pent-up stress along fault lines, often imperceptible in isolation yet cumulatively remolding the landscape over eons. Sedimentation deposits layers of rock that quietly preserve fossils and chemical signatures, creating a record of climatic shifts, mass extinctions, and biological innovation, a narrative of slow transformation embedded in stone. Glacial movements and polar ice come into focus, shifting imperceptibly over millennia. Ice sheets in Greenland and Antarctica advance and retreat, carving valleys, depositing moraines, and influencing sea levels in subtle, patient increments. Seasonal snow and ice form and melt across latitudes, reflecting sunlight, regulating temperature, and serving as a slow-moving record of atmospheric conditions. Turning attention to Earth's hydrologic cycle, rainfall, evaporation, and groundwater flow interconnect in delicate balance. Rivers trace valleys with patience, deltas form slowly where sediments meet oceans, and aquifers store water for centuries. Each droplet participates in a continuum that supports life, sustains ecosystems, and regulates temperature, all unfolding quietly and unhurriedly, almost invisible in the passage of a single human lifetime. A drifting focus moves to Earth's magnetic field, generated by movements in the liquid outer core. This field deflects solar wind, guiding charged particles toward the poles to produce auroras that drift slowly across the sky. Magnetic reversals, occurring over tens of thousands of years, leave traces in rocks and sediments, reminding us that even invisible forces on Earth move with patient, imperceptible grace. Human presence emerges softly in thought, an agent of change interacting with geological, atmospheric, and biological processes. Cities grow, agriculture reshapes landscapes, and industry affects air and water, yet these influences operate within a vast system governed by slow feedback loops. Climate, ocean currents, and ecological networks respond over years and decades, illustrating the temporal scales that exceed daily awareness yet shape planetary behavior in profound, patient ways. The Moon drifts gently into attention, Earth's companion in an orbital dance lasting billions of years. Its gravitational pull governs tides, stabilizes axial tilt, and influences rotational rhythms. The Moon's phases wax and wane slowly, shaping nocturnal light, while subtle geological processes, including the formation of maria and impact craters, unfold on scales measured in millions of years. Its quiet companionship underscores the planet's rhythms and the unhurried elegance of celestial mechanics. Earth's atmosphere invites consideration of chemical and thermal dynamics, from ozone layer interactions with ultraviolet radiation to slow variations in greenhouse gas concentrations. Atmospheric circulation moves air and moisture in patterns of jet streams, trade winds, and cyclones, each process balanced delicately by solar input, Earth's rotation, and surface features. Changes may occur slowly or abruptly, yet the system exhibits a resilient equilibrium, adjusting imperceptibly to maintain habitability over geological spans. The tectonic canvas floats into reflection, continents shifting, colliding, and rifting over tens of millions of years. Mountain ranges like the Himalayas rise as plates converge, while rift valleys slowly separate continents, oceans widening with patient inevitability. Volcanoes release gases and lava, reshaping local and global conditions, yet the processes are gradual, often imperceptible without precise measurement instruments, revealing the enduring yet subtle nature of planetary transformation. Patterns of climate drift into focus, governed by axial tilt, orbital eccentricity, solar irradiance, and oceanic feedbacks. Ice ages advance and retreat over tens of thousands of years, deserts expand and contract, and ecosystems migrate in response, all unfolding slowly, gently altering the character of the planet in ways almost imperceptible to a human lifetime. Each season, decade, and millennium contributes quietly to Earth's narrative, a continuous, unhurried symphony of environmental change. Finally, or rather with gentle patience, attention turns to Earth's interconnected cycles, biogeochemical flows, hydrologic movements, tectonic shifts, and climatic rhythms. Each element interacts subtly with others, forming a system that is self-regulating, complex, and slow to change. Observation of these patterns requires time, instruments, and reflection, as the most profound truths of Earth's behavior are revealed not in fleeting moments but through the accumulation of years, decades, and centuries of patient study. A quiet glow of thought drifts gently over Venus, the second planet from the Sun, orbiting at roughly 0.72 astronomical units. Sunlight arrives in just over 6 minutes, interacting with dense clouds of carbon dioxide and sulfuric acid to maintain a slow, persistent greenhouse effect that has shaped the planet over billions of years. Venus follows a nearly circular path, its axial tilt of just 2.64 degrees creating minimal seasonal variation, resulting in a surface of remarkable thermal uniformity. History whispers softly across time, recalling that Venus has fascinated humans since prehistoric observation. Known as the morning star or evening star, it was noted carefully by Babylonians, Mayans, and Greeks, its brilliance inspiring myths and symbolic associations. Telescopic studies in the 17th century revealed its phases, gradually unveiling its true planetary nature and unraveling the mysteries of its steady luminance with quiet persistence. A subtle drift of reflection moves toward Venus' unusual rotation. Unlike most planets, it spins slowly in a retrograde direction, completing a full rotation in 243 Earth days. Its day therefore exceeds its year, which lasts about 225 Earth days, producing an extraordinary rhythm of sunlight and shadow. This leisurely rotation, combined with dense atmospheric super-rotation, drives winds that sweep around the planet in just a few Earth days, a paradox of slow and fast processes coexisting harmoniously. Turning attention upward, Venus' atmosphere emerges as a thick, almost suffocating blanket composed primarily of carbon dioxide, with high clouds of sulfuric acid suspended above the surface. Surface pressure is immense, about 92 times that of Earth, while temperatures reach roughly 465 degrees Celsius, enough to melt lead. These extreme conditions are maintained quietly by the greenhouse effect, while subtle chemical and electrical processes in the clouds unfold over eons, measured patiently by orbiters and landers. Across the shrouded surface, radar mapping reveals vast volcanic plains, mountain ranges like Maxwell Montes, and tectonic features such as Coroni and Tesserae. Lava flows stretch across silent expanses, recording internal heat release and slow mantle convection over geological time. Impact craters are sparse, erased gradually by resurfacing events, each process unfolding with patient, almost imperceptible motion across the planet's crust. Volcanism whispers gently through Venus' past, leaving ridges, domes, and basaltic plains as testament to slow geological change. Evidence hints that activity may continue today, with subtle variations detectable only in atmospheric composition or surface emissivity. The gradual movement of magma beneath the crust contributes quietly to thermal balance and episodic gas emissions, maintaining a steady geophysical rhythm. Considering its magnetosphere, or the notable lack thereof, Venus presents a different story. Lacking a significant intrinsic magnetic field, it experiences direct interaction with the solar wind, which gradually strips hydrogen from atmospheric water molecules over billions of years. This slow process has quietly sculpted Venus' present atmosphere, a testament to the patient work of cosmic forces across deep time. Exploration drifts into memory, recalling the meticulous work of Mariner 2, Venera, Pioneer Venus, Magellan, and Akatsuki. Each mission unveiled layers of Venusian mystery, mapping topography, analyzing atmospheric composition, and observing cloud dynamics. Venera landers briefly survived on the surface, transmitting data and whispers of temperature, pressure, and chemistry, each measurement patiently recorded before the probe succumbed to the extreme environment. Atmospheric dynamics reveal a curious rhythm, with super-rotating winds circling the upper layers up to 60 times faster than the planetary surface below. Winds exceeding 360 km per hour shape rapidly moving cloud patterns, while the surface remains almost motionless, producing a mesmerizing contrast of fast and slow motion observed with patient measurement over decades. Hints of ancient water drift quietly and isotopic ratios of hydrogen and deuterium, suggesting Venus may once have hosted oceans or lakes. The runaway greenhouse effect slowly evaporated and dissociated these waters, allowing hydrogen to escape to space, transforming the planet from a once potentially habitable world into the furnace we observe today. Cloud chemistry floats into thought, sunlight breaking down sulfur dioxide and other trace gases, forming thick sulfuric acid clouds. Lightning is infrequent yet detectable, moving slowly within the dense layers. The clouds reflect much of incoming sunlight, maintaining a high albedo and insulating the surface, quietly balancing energy across Venus with patience stretching over eons. Thermal constancy emerges, as temperatures remain nearly uniform between day and night due to slow rotation and efficient heat transfer through dense atmospheric layers. The planet's unchanging warmth creates a stillness that, though extreme to humans, exemplifies the slow and persistent equilibrium maintained by Venus for billions of years. The gravitational relationship between Venus and Earth drifts softly into consideration. Close approaches, occurring roughly every 584 days, follow predictable patterns, contributing to long-term orbital stability. These interactions unfold without drama, a slow cosmic rhythm observable only through careful calculation and patient observation. Thought drifts toward the future of Venus exploration, imagining robotic landers, orbiters, and aerial platforms studying clouds, topography, and geochemical cycles. Each mission proceeds cautiously, gathering data slowly and methodically, uncovering secrets piece by piece, allowing Venus' quiet majesty to persist as human curiosity extends outward in deliberate, measured steps. A faint shimmer of thought drifts over Mercury, the smallest of the terrestrial planets, orbiting quietly at an average distance of about 0.39 astronomical units from the Sun. Sunlight reaches this planet in just over 3 minutes, casting a quick, piercing illumination over its cratered surface, while temperatures swing dramatically between approximately 430 degrees Celsius during the day and minus 180 degrees Celsius at night. Its orbit, the most eccentric of any planet in the Solar System with an eccentricity of 0.2056, produces slight variations in solar distance that subtly influence the pace of sunlight striking its surface. Mercury rotates slowly, completing one rotation in about 58.6 Earth days, while its year lasts only 88 Earth days, creating a curious resonance in which 3 rotations coincide with every 2 orbits, producing a rhythm unique among planets, a subtle beat of celestial mechanics quietly unfolding over time. A gentle murmur of history glides into awareness, reminding us that Mercury has been observed since antiquity. Ancient Babylonian and Greek astronomers noted its swift movements across the dawn and dusk skies, often attributing symbolic significance to its fleeting appearances. The invention of telescopes revealed more subtle details, including its crescent phases, and careful observations of its orbit exposed a precession of its perihelion that would later perplex scientists for centuries until explained by Einstein's theory of general relativity. Each incremental discovery added layers of understanding, a patient accumulation of knowledge tracing the planet's steady yet elusive path in the heavens. A soft reflection unfolds upon Mercury's surface, revealing a world densely marked by impact craters, resembling a miniature moon in its topography. Vast basins, such as Eris, stretch across thousands of kilometers, their rims and interiors slowly shaped by subsequent impacts, lava flows, and tectonic adjustments. Interspersed are smooth plains, likely formed by volcanic effusions, and scarps created by the planet's gradual cooling and contraction over billions of years. Every crater, ridge, and basin records an ancient narrative, a slow chronicle of cosmic collisions and geological responses, preserved for patient study by orbiting instruments and imaging systems. A quiet current of thought drifts toward Mercury's exosphere, a delicate, almost ephemeral envelope of atoms rather than a substantial atmosphere. Composed primarily of oxygen, sodium, hydrogen, helium, and potassium, it forms through processes like solar wind sputtering and micrometeoroid impacts. The thinness of this layer, less than a trillionth of Earth's atmosphere by mass, means it cannot distribute heat or support weather, yet it interacts with the solar wind to produce faint, slowly shifting phenomena detectable only by precise instruments. In this near vacuum, every particle moves according to the strictest rules of motion, its behavior a subtle, continuous ballet shaped by radiation and gravity. Turning attention inward, Mercury's internal structure reveals a surprisingly large metallic core, accounting for about 85% of its radius. This iron-rich core generates a weak magnetic field, approximately 1% as strong as Earth's, aligned nearly perfectly with the rotational axis. Surrounding the core is a silicate mantle and crust, relatively thin, with evidence of past volcanic activity and tectonic adjustments. Cooling of the core and mantle has produced global contraction, forming lobate scarps and cliffs that stretch hundreds of kilometers. These internal processes proceed slowly, imperceptible to the naked eye, yet they leave tangible traces across the planet's surface, whispering the quiet history of planetary evolution. A subtle ripple of reflection drifts toward Mercury's orbital peculiarities. Its high orbital eccentricity produces variations in solar intensity that are small but measurable, while its 3-2 spin orbit resonance creates a delicate interplay between rotation and revolution. These factors contribute to unusual patterns in solar heating and illumination, causing temperature extremes that shift across its long days and nights. Mercury's movement is a precise, patient dance, dictated by the gravitational pull of the Sun, resonating with the rhythms of the entire inner solar system in a slow, meticulous harmony. A soft drift of thought moves to the magnetic field, weak yet present, revealing the ongoing motion of molten iron in the outer core. This dynamo effect is small, yet it interacts with the solar wind to form a magnetosphere, deflecting some charged particles and shaping bow shocks in the surrounding space. The field's presence is detectable only through careful spacecraft measurements, a whisper of internal activity maintaining a subtle protective envelope around the planet. These interactions unfold without urgency, a patient modulation of magnetic and solar forces quietly sculpting the space around Mercury. Attention meanders toward the surface composition, revealing silicate rocks rich in magnesium and iron, interspersed with trace elements like sulfur and potassium. Spectroscopic analyses indicate that much of the crust is ancient, dating back to the earliest periods of the solar system, while smoother plains likely formed from effusive volcanism billions of years ago. Microscopic layering of minerals records the slow cooling and chemical differentiation that occurred after planetary accretion, a delicate chronicle of planetary history written in the language of stone. The planet's surface, despite its stark appearance, holds subtle variations in albedo and composition, each detected with patient observation. A subtle awareness drifts to Mercury's temperature extremes, remarkable for their intensity. Daytime heat melts lead and bakes the regolith, while nighttime cold plunges into the realm of cryogenic conditions. These changes, though abrupt in human perception, occur predictably according to the planet's slow rotation and lack of atmosphere, a steady pattern of thermal swing observed over centuries by astronomers and over years by spacecraft. The extremes underscore the delicate balance maintained between illumination, rotation, and the absence of a moderating atmosphere, a rhythm both harsh and meticulously ordered. A soft current of thought glides to Mercury's exploration history, beginning with Mariner 10 in the 1970s, which performed multiple flybys to map nearly half of the planet's surface. Observations of topography, magnetic fields, and exospheric composition provided a patient foundation of understanding. Decades later, the Messenger mission orbited Mercury from 2011 to 2015, delivering comprehensive mapping, chemical analysis, and magnetic field measurements. Each dataset built upon the previous, slowly revealing a planet that, though small and seemingly inert, contains a wealth of subtle, dynamic processes and a remarkably large core relative to its size. Turning thought gently toward Mercury's orbital companions, one notices the occasional meteoroids and dust particles that collide with its surface, forming microcraters and contributing to its tenuous exosphere. Solar tides tug delicately on the surface, influencing long-term stress patterns in the crust, and the planet's proximity to the Sun subjects it to intense radiation and charged particles, slowly etching chemical and physical changes into its surface over millions of years. These quiet, persistent processes produce a continually evolving planetary exterior, observable only through careful, patient measurement. A gentle, drifting contemplation turns toward the role of Mercury in the broader solar system. Its proximity to the Sun influences its orbit and contributes to the stability of interplanetary dynamics. Resonances with Venus and Earth create subtle gravitational interactions that modulate long-term orbital evolution. These effects, though imperceptible to daily observation, reflect the patient and intricate interplay of celestial bodies, a reminder that Mercury's quiet presence exerts influence far beyond its small size. A subtle meandering of thought arrives at Mercury's impact history, densely cratered with records of ancient collisions. From the vast calorous basin to countless smaller craters, each impact has redistributed surface material, produced ejecta patterns, and contributed to tectonic adjustments. Over eons, the planet's surface has been sculpted into a mosaic of ancient history, a slow narrative captured in the quiet arrangement of rock in regolith, patiently observed and measured by spacecraft instruments. A soft awareness drifts toward the solar wind's persistent influence, which gradually erodes surface materials and energizes the exosphere. Sodium, potassium, and other volatile atoms are stripped away, joining the space environment in a subtle, continuous flow. These processes, unfolding over billions of years, contribute to Mercury's evolving chemical balance, a reminder that even small planets experience the patient shaping hand of stellar forces across vast temporal scales. Now, my listener, you may not care. And that is completely fine. You need not remember numbers, distances, or icy reflections. The planets will remain in its orbit whether you think of it or not. It is there, some moving so slowly that sometimes one human lifetime is only a fraction of its year. Isn't that truly amazing? If your eyes are closed, if your thoughts are drifting, then my job here is done for today. Thank you for spending this unremarkable moment with me. You have listened to The Sleepy Sloth, where uninteresting things become the softest lullabies.